Folks, looking at class number 38, our goal is to label the velocity at different points on an angled projectile. So the do now is just kind of review of horizontal projectiles and vertical projectiles. So let's get that done first. So draw a little picture here. So we have a horizontal projectile fired from a cliff. So here is my cliff. Right, that cliff is 35 meters tall, and it's fired at 24 meters per second. All right, so we have a ton of information here to start. So let's start in the x direction. We always know that our x acceleration is 0 meters per second squared because there's no force in the horizontal direction after it's launched. Our velocity in the x direction is 24, and it doesn't change. Distance in the x direction we don't know, and time for the x direction we don't know either. In the y direction, we always know that our acceleration is 9.8 meters per second squared because that is the force in the y direction. Our initial y velocity is 0 because initially all of the velocity is pointed in the x direction. We don't know the final y velocity, though it will increase as time goes on. We know the y distance as well. Look at 35. That's a vertical distance, so that's in the y direction. And we don't know time either there. So how long will it take, or will it be in the air for? So it's probably easier to use our y direction for this, and it is. So let's see. We have the equation. Let's see. We don't have VF, and we don't have T. So an equation without VF that we could use potentially is this one here. So step one, D equals VIT plus 1/2 AT squared. If you don't know what that equation is, know where it is on your reference table, please. We have 35 meters, so I'm going to leave the units out just to clean it up a little bit. V initial is going to be 0 because we're looking at the y direction. T, well, it doesn't matter. That's 0. That goes away. Plus 1/2, 9.8 t squared. All right, so we have 35 equals 4.9 t squared. Divide both sides by 4.9, take the square root of both sides. You should get that t is 2.7 meters. So that goes right over here. So that is our time for both the x and the y. So now the distance from the cliff, that is our x distance. All right. So we can use the same equation if we like, or we can use v equals d over t. Either one will work. So let's do the same equation, but now we're in the x direction, just to show that it is different. Right, so d is going to be our unknown, v initial is going to be 24, t is going to be 2.7, plus 1/2, a in the x direction is 0, t is 2.7 squared. Well, that doesn't really matter, that all goes away. We end up getting a distance in the x direction of about 64 meters. All right, so there we have it. That would be this distance here. So it went 64 meters from the base of the cliff. It was in the air for 2.7 seconds. All right, let's check out the next one. This is a vertical projectile. So we have a projectile that is fired straight up into the air. So VI is 23 meters per second, goes up, 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 and it comes back down. But we'll pretend the final position is up here. That way we know that the final velocity is going to be 0. That's a really convenient trick to do, and I always recommend doing it. This object is not moving in the x or y direction, excuse me, in the x direction at all. So these are all 0. Okay, it's only moving in the y direction. So we know v initial y is 23. We know v final y, excuse me, gotta fix that. Y is 23. V final y is 0. The acceleration we know is going to be negative 9.8. Why is it negative and not positive? Because the acceleration is hurting the initial velocity. Okay, d we don't know, time we don't know, velocity reaches the ground we don't know either. So let's find max height. That's going to be the distance in the y direction. So we don't have time, so the one equation without time we could use is vf squared equals vi squared plus 2ad. Vf is going to be 0, vi is going to be 23 squared plus 2, negative 9.8, and that's d as well. All right, d ends up being 27 meters. So that was the first thing we did. This is 27 meters. So now we can use that if we wanted to find the time, but we don't need to. So to find the time to the apex, that's when the velocity is 0, the y velocity is 0. So we could use vf equals vi plus at. So Vf is 0, Vi is 23, plus negative 9.8 t, and t ends up being, this is a little bit rounded, but 2.3 seconds. To get the total hang time, you simply, so this is, we'll put 2.3 seconds here. To get the total hang time, you just multiply it by 2. Time up equals time down, so a total of 4.6 seconds. And the velocity when it reaches the ground, well, the velocity it reaches the ground with is the same velocity it was thrown upward with. So just opposite direction. So it's going to be 23 meters per second downward, or you could say negative 23 meters per second. Either one works. All right, so more quick review on breaking a vector up into x and y components. So we have this vector here, 15 meters per second, an angle of 28 degrees. So this is Vx. and this is Vy. Okay, I'm going to call this V initial Y because the velocity in the Y direction does change, in the X direction it doesn't change. So in the X direction, that's the adjacent side, so that's going to be, you can use the equation AX equals A cosine theta. So it's going to be 15 cosine of 28. Make sure you're in degrees mode, and you should get 13.2 meters per second. In the Y direction, again, this is the initial velocity in the Y direction because it does change. We know AY equals A sine theta. So that's equal to 15 times the sine of 28 degrees. Make sure you're in degrees mode. That's about 7 meters per second. Right, so now here's an angle projectile question. We're not even going to finish it in this class. We'll do it in class 39, but let's just start it here. So we have a golf ball and it's chipped. I got the launch angle, I got the launch velocity. A few different ways to start this, but I think the easiest way to start it is to get the Vx and Vy, which we just did, but these numbers are obviously different, so let's do that now. So this is going to be Vx, so this is going to be 15 cosine of 56, because it's the adjacent side. And this is going to be 15 sine of 56, because it's the opposite side. All right, so let's really quickly calculate those. So I have 15 cosine 56. That comes out to be 8.39, or we'll call it 8.4. It's a little bit rounded, but that's okay. 8.4, so that is my x velocity. All right, let's do 15. Oh, sorry, it's not 15, it should be 5. Let me erase that, apologize for that. I got mixed up with the last question. So let's fix this. This is 5, and this is 5. So let's do 5 cosine 56. 2.8. That looks a little bit better. So that's the x component of velocity. And 5 sine of 56. That's 4.15. Again, a little bit rounded, but that's okay. Okay. So it says draw the trajectory of the golf ball. Use all the space, label your initial position, label V initial Y and Vx at the initial position. So let's draw the ground really quickly. Here's our ground. Here's our golf ball at the initial position. Ball goes through the air. All right. So we have the initial position. V initial Y, we just said was 4.15 meters per second. And Vx, you said, was 2.8 meters per second. So let's talk about the apex now. At the apex, the x component of velocity does not change. That is still 2.8 meters per second. But the y component does change. V final y, or Vy up here, is going to be 0 at that point. But the x component is still there. So why doesn't the x component change? Because there's no net force in the x direction, only the y. Excuse me. So E, it says, what is the vertical component of the velocity the instant before it lands? Well, we know the x component before it lands. That's the same. That doesn't change. That's actually question F, 2.8 meters per second, because there's no force in the x direction. But the y component now is going to be negative 4.15 meters per second, or 4.15 meters per second downward. All right. And again, the reason the x component does not change is because there is no force in the x direction. There's only no force in the y direction. That's why the y velocity changes, the x does not. So we know the acceleration in the x direction is 0, and the acceleration in the y direction is negative 9.8 meters per second squared. So let's throw that in our chart as well, that we're not doing all the math today. All right. So again, since F net in the x direction is 0, the acceleration in the x direction is 0. Since F net in the y direction is equal to the force of gravity, the acceleration in the y direction is equal to little g. So just a little concept question. At what angle does the ball approach the ground? Label it. What is the magnitude of the velocity the ball lands with? So there's some beautiful symmetry to this question. If an object is thrown at 5 meters per second at an angle of 56 degrees. It goes through the air. When it lands, as long as it's landing at the same height, it's still going, or not still going, its velocity is now 5 meters per second, and its angle is 56 degrees. Its velocity did change throughout the whole flight, but when it lands, it has the exact same velocity it has when it was launched and approaches at the exact same angle. All right, so there's class number 38. We are going to actually solve the rest of this question in class number 39. Have a great day, everybody.